All right, welcome to the first of the 2015-2016 Google Hangout seminar series hosted here at the University of Central Arkansas. This seminar series is supported by a grant from the University of Central Arkansas Foundation. Very thankful for their continued support to bring these seminar series to our students. We have the pleasure to welcome Dr. Milton Garcia. He is a physics major. He got his BS in physics from the Florida Institute of Technology in 1989. He then went on and got his PhD in oceanography from the University of California at San Diego in 1995. He then specialized further as a postdoc in volcanology at the University of Alaska at Fairbanks at the Scripps Institute of Oceanography. He is currently an associate researcher at the Hawaii Institute of Geophysics and Planetology at the University of Hawaii. I'm very pleased to welcome Dr. Milton Garcia, and his seminar is entitled Extreme Infrasound. So please take it away, Dr. Garcia.
Aloha. So the first thing I want to leave you with is the idea that we are immersed in a fluid. Now, can you hear me okay on that end?
Yes.
Good. So we are completely surrounded by this fluid that is constantly vibrating. And I'm going to ask you to take a moment to listen. Just listen to the world around you. So the first question is, can you hear me? Not yes or no, yes. So for the next few minutes, my voice should be your primary acoustic signal.
Yeah.
So the next question is, what is the quality of this signal? Is it accented? Yes. That accent might be described as Caribbean Spanish inflection. It's everywhere. And you all have to compensate a little bit. You have to adjust with that particular sound quality. And at the end of the day, we all have an accent. Wherever you go, you'll be recognizable as an American accent or a particular Arkansas accent or whatever you're coming from. Second question, is it intelligible? Can you hear the vowels and consonants? And that depends on many factors, including what is the ambient noise. Now, listen to the noise around you. There's a few ways we can do this. There's many ways of listening. What I'm asking you to do is the monitoring mode, where you immerse yourself in the environment that you're sitting in, and you look at all the different noises. You have an air conditioning system. Is it interfering with the voice primary signature? That is your ambient noise. You're trying to characterize that, and your brain and your ear automatically compensates for that. Now, the other thing that you may do is diagnostic. If you have control over your environment and you're getting noise from the hallway, you might recognize, oh, there's a problem over there, so you could consider closing the door. Or the AC is interfering too much, you can turn off the AC. And you can actively start acting towards exploratory listening, where you close the door, is that better or worse, and you open it again. If you have a mixer on your end, you can adjust different frequency bands and kind of pretty much mix it. If you wanted to explore even further and you were musically inclined, you can start recording, dubbing, and repeating and create a musical composition out of this live environment. You can add echoes and flange. You can add a wah-wah pedal. You can do anything. That becomes a synthetic type of listening, where you're taking a sound field and you're modifying it, and you're even creating something that is not there, but somehow provides additional information. Once you go through the life cycle, you go and immerse yourself in the sound field again. And we do this automatically. We go through the cycle of listening, experimenting, adjusting, and our brain does this in real time. And those of us who have the tools and technology to do so can also do that digitally. So for infrasound, this is sound that is below your hearing threshold. So in principle, you cannot hear it, but you can feel it. So I'm going to ask you to immerse yourself in the environment around you and essentially look for a physical sensation of vibration. You might get the sensation when you slam a door, for example, that startling feeling that you get. You can feel it sometimes through your skin. It's a vibration of AC systems, usually have that. And the main concept here is that you cannot hear infrasound, but you can sure feel it when it's loud enough. It physically moves you. It's a physical oscillation of the air, atmosphere, and your body around you. So we're going to look for very low frequency sound propagating through the atmosphere. And the main thing to bear in mind is that the things we're looking for are changes. So you have this ambient field right now, and you're sitting on it. It's peaceful. I'm assuming nothing's blowing up around you, but if something were to blow up, that's what we're looking for. We're looking for changes, delta T's. Delta P, the change in pressure over time. So we're looking for variability in the acoustic sound field. And we're looking at some of the primeval sources of sound. These things precede us as a species. We evolve in conjunction with the sound from the ocean. We came from the ocean. So we have big waves, we have tsunamis, meteors, things impacting Earth. This is how water came to our planet. So we've definitely evolved with these environmental sounds. Volcanoes, of course, that is something that provide fertile soils. This is how we grow our vegetables in many places, because they provide a growing environment. And hurricanes, severe weather, nobody escapes that. Weather always hits you. And essentially, you can characterize a weather system by the pressure changes that go in there and the wind fields around them. And so these are some of the events that create low-frequency sound in the atmosphere. And they are very large scale. Now, you're all physics students, so you're familiar with the concept of a wavelength. And I'm going to introduce wavelengths that are much, much larger than humans. And that's one of the recurring features of infrasound. It's just big, bigger than humans. Our problem with infrasound is that the medium through which we're propagating is always changing. And this is something that, most wave propagation environments, you don't worry about them. Light, it's so fast that things don't change that much with it. Same with seismic. The solid Earth doesn't change that much. The ocean changes slowly, but the atmosphere is constantly changing at all time and spatial scales. And so what I'm showing you over here is some of the variability that you have in the atmosphere, all the cloud formations that you see. Every time you look at a cloud and it's rippling and weaving, that is a change in density, in temperature, in wind velocity, just creating all these corrugations. And so I introduced to you the concept of a wavelength, which is the scale of a wave, the physical scale. And it's usually symbolized by lambda. In this case, you're looking at gravity waves in the atmosphere. And the interval between those two crests, shown in the on the upper right side, is the wavelength of it. And you can measure it in, hundreds of meters to kilometers. Now, another wavelength will be the one right below that, where you see the waves breaking. And you get that kind of breaking wave whenever you have a big density difference between materials. An example would be the ocean surface and the atmosphere. It's so different that, waves break in there. And so you can have the same thing in the atmosphere whenever you have a change in the density and speed of the wind aloft. So you get breaking waves up in the upper atmosphere. And so the concept that I want to introduce you is the effective speed of sound in the atmosphere. It's the wavelength times the frequency, F is the frequency, times the velocity of flow of the atmosphere. And that can be on the scales of hundreds of meters per second, which is a portion of the atmospheric sound speed. Now, I'm assuming you guys are familiar with the concept of wavelength. Now you can introduce in frequency, also very accessible. I am speaking to you in an audio frequency, on the orders of hundreds to thousands of cycles per second, or hertz. And that is a quantity that in a linear system is conserved. we're not going to assume linearity, but it's something that you are familiar with because we use it all the time for communication. And the harmonic structure of the frequency is what give each voice a type of fingerprint, ability for you to recognize your mother from your grandmother, from your sister, from your brother. Is the timbre of that sound, is the spacing of frequency components in the frequency domain. And so what you're seeing now is you're familiar with the wave propagation of a type of thing. Light, for example. Speed of light, 3 × 10⁸ meters per second. And you get optics whenever you have a change in the refraction index. We have the same in the atmosphere, where the change of the refraction index depends on the wavelength and the frequency, or the temperature of the atmosphere, and then the speed of the wind aloft, which means that it changes whichever way you look. If you're going downwind, you get one refraction level, and you go upwind, you get a different refraction level. The figure at the very bottom shows you what happened with sound when a spacecraft blows up. In this case, that's the Columbia shuttle, when it blew up on its entry from Texas, over Texas. And you get acoustic energy trapped up in the stratosphere. You can see that's where all this banding happens, because there's a low temperature zone in there. And you also can have energy trapped in the upper atmosphere, in the thermosphere, and it bounces right back down. So those are acoustic lenses in an atmosphere. So this is essentially an introduction to how sound propagates in the atmosphere and the relationship between temperature, velocity, aloft. So let's go back a little bit in time, how we used to do this before the digital technology came in. We're all born with 2 sensors in our heads. So we have 2 microphones, we call them our ears, and they give us the ability to go side to side. So you're all facing me, and that's because your ears align for the time of travel, and the wavelength of this audio wave scale with the size of your head. So this is why we communicate in this range. If we communicate deeper like elephants, you need a bigger head and bigger ears. Now, we only have 2 ears, so to tell back and front, the shape of our ears help us discriminate between forwards and backwards radiation. Now, if our ears were just little holes in our head, then we'll need 4 of them. So when you look at the guy on the upper left, he's basically expanded his head, right? So now he can go lower in frequency, and he's listening for planes from World War I and World War II that will come over and bomb Europe. And so there was spot a guy sitting out there, you see on the left-hand side, with ear extenders. And he's got 1 left and right, that gives you left and right, and then he's got 1 top and bottom. It tells you how high the plane is coming through. And so they used to post these guys listening for incoming. And in England, they got even fancier. They built giant walls, essentially big parabolic dishes, to concentrate the sound. And they had a guy sitting in the middle listening all night long for incoming German planes. And if something happened, they issued a siren, right? Hit the shelters. And so this is the kind of, this is what we had to do back in the day of purely analog technologies. Spot a guy listening. Now, things have changed since then. And I'm showing you a station that we built in Diego Garcia, the British Indian Ocean Territory, essentially the middle of nowhere, 7 degrees south, somewhere between Africa and Indonesia. And it consists of 24-bit digitizers with high-resolution pressure sensors. And we deploy these listening stations as arrays. You remember how that guy sitting there with the 4 extensions? Those were 4 elements. Well, this is 7. And it allows you to, again, look at high resolution of direction of arrival. It tells you how fast a signal is moving, and it tells you where it's coming from. This is one of the stations of the global infrasound network of the Comprehensive Nuclear Test Ban Treaty. And we use this network to monitor for clandestine nuclear tests. Essentially, we're listening continuously on the whole planet. And this is an image of the extent of the network close to today. 2013, where we had a large meteor coming, the Chelyabinsk meteor over Russia. And I'll talk a little bit more about that. And the yield equivalent of that explosion is about half a megaton of TNT. For nuclear, it's actually twice that. So it's equivalent to about a megaton yield nuclear explosion over the atmosphere. And it got picked up by 20 out of the 42 stations in the global network. And we're going to discuss this a little bit more detail as an example of a calibration shot that nature provided for us. Now, one of the latest evolutions, any of you who have iPhones, iPads, or iPod Touches, there's an app for this. So any of you can record infrasound with your sensors. Just download it from the App Store. It's free. And then you can record the infrasound as well as analyze it with the second app. So this brings about a substantial change in potential coverage globally of infrasound and for looking for natural hazards applications. So now comes a series of case studies. Now volcanoes, what makes volcanoes blow? Well, they're under pressure. You have all this gas under pressure, and whenever water expands, there's a 1,000-fold expansion in volume, and that is one of the things that makes volcanoes blow up. You uncork them, they expand very quickly, and off they go. And so infrasound is a very natural way to measure volcanic eruptions. And one of the important applications is that planes don't like ash, volcanic ash in particular. If you're flying over an ash column and the ash gets into your jets, it will often melt, seize the engines, cause substantial damage. And there's been many cases where the plane begins to crash. Some of the instances, all the engine ceases and it starts going down, it cools and it breaks and some of the engine starts, but the cost of the engine repairs and the abrasion of the glass is substantial, and the cost of potential loss of life because of ash and aviation is significant. So it's a very pragmatic application for any of those who've ever been on an airplane. So let's look at some examples. Now, Hawaii is a very nice volcano. It moves slowly. It's a good way to test things. So you can see lavas, it just moves around and sloshes around. And sometimes it can be very musical. I don't know if this is going to work, but we'll try it anyway. Let's see how you tell me how it sounds over there.
Can you all hear it? No, very, very difficult to hear the low.
So I'll skip the sounds from now on. Unfortunately, but a lot of this stuff is on SoundCloud, so you can go to iSound Hunter and get some of the sounds from there. Sometimes some of them are really musical. You have essentially reverberation of harmonic systems, and some gentleman, Jason Thompson, got inspired to make a musical composition and percussion for that. But some of them are more impulsive, and since the sound doesn't work, what I want you to watch is this is the infrasound on the lower scale, and the video time synchronized on the upper scale. And as you can see, a few minutes into the record, you're going to get the oscillation coming from the infrasound. I want you to look at the video how you can actually see the sound altering the steam cloud. And watch for it, wait for it, and here it goes. So you could see the oscillation on top of the steam cloud as it bounces back and forth, and that's what sound is. Sound is essentially oscillation around the center point, and in this case, it's superposed on top of a flow, the flow speed of the steam vent. Now, other things can also produce sound, and again, we had a scenario where the earth split open and lava came out of the ground, and it just started flying up in the air and generating a lot of sound. So we had lava fountains coming up, and that was very spectacular, but it was a big fissure eruption, so it's hard to figure out where things were. And what we could see is things bouncing back and forth between one side of the fissure and the other side of the fissure. So this is an example where you can use infrasound to tell you, okay, this is where the activity is on one end and versus the other end of the fissure. Now, this is an audio one, and you can see it on YouTube. It's a Hawaiian bass drop. I'm not too sure if you can hear it, but essentially it's a sound synchronized with the collapse. So not only things that blow up, but also things that collapse. Any changes in volume or velocity can generate an acoustic signature. And this is equivalent to a collapse, and then an expansion. And if you go to YouTube, you can actually hear this with some good subwoofers or good headphones. So the natural extension is, okay, so the small eruptions are fairly benign, all things considered, but there's some monsters out there. There's some really nasty eruptions. And so we went to Ecuador and deployed 2 arrays, one near the Colombian border and one by Riobamba, to monitor the whole country of Ecuador. And Tungurahua volcano was kind enough to do a Plinian eruption that we captured in its entirety. What that allowed us to do is essentially capture the acoustic fingerprint of a big eruption, what we call the Plinian eruptions. This became very handy because it really simplified the problem. See, the little things are hard to catch, but the big things, the full-on screams of fury, they actually have pretty unique signatures. And again, you're moving multiple standard deviations away from a little eruption type. It's its own set of physics. It's highly nonlinear. You're looking at massive jets, hundreds of meters in diameter, injecting ash above 10 kilometers. So you just have massive amounts of material moving at high velocities. And that generates its own signature that's very deep. So this was a way forward for us. It allowed us to say, oh, okay, let's look for the big boys then. Kelut volcano in Indonesia erupted in 2014. And that one injected ash to 20 kilometers, big explosion. And you have another type of waves. Acoustic waves are compressional waves. You squeeze them and then bounce back. Gravity waves are more like you move something forward, it bounces back. And you see this in the ocean or in a lake when you drop a pebble in it.
So we lost you there for a sec. Milton, could you go back just a bit?
Sure. So back to Kelut volcano in Indonesia, injected ash to 20 kilometers. And generated not just acoustic waves that are compressional waves, you squeeze things and it bounces back, but also gravity waves, which is what you will see in the ocean. You're seeing legs when you drop a pebble. Something moves up, something moves down, it compensates with gravity. So you can see on the right bottom side, the gravity waves being generated by this giant eruption that injected ash to well above cruising altitudes. And where you fly is 30,000 feet. That's around 10 kilometers. So anything above 10 kilometers, it's like a big hazard to ocean aviation because it stays out there for days. Well, there's another set of waves called acoustic gravity waves, which are somewhere in between gravity waves and acoustic gravity waves because they're both extremes. Acoustic waves are on the high frequency, gravity waves are on the low frequency, and acoustic gravity waves are a combination of both. Our colleagues in Singapore did a very nice study where they took all the seismic stations they can get their hands on and look at both the seismic and acoustic arrivals associated with that explosion. And the main point here is that once things go deep enough and big enough, the whole planet is connected. Ocean, solid earth, atmosphere, heck, even the ionosphere, the whole thing starts ringing. It's big enough that everything becomes connected. So in this particular explosion, it was big enough that what you're seeing is the little blue triangle is the volcano. And you're seeing a seismic arrivals coming in with all the nearby seismic stations, as well as some of the infrasound stations that are part of the global monitoring system. And when you look at the lower right-hand side, you can see that it went pretty much all over the world. You can see this explosion in Indonesia, picked up in Alaska, in Hawaii, in Europe, South Africa. And so when you go deep enough, it's hard to stop the sound. It just keeps going. And it will go around the world a few times, as I'll show you a little bit later. We're going to switch a little bit to ocean acoustics. The infrasound technology is part and parcel of volcano monitoring now, and but not so much part of oceans yet. And there's a few interesting possibilities in here. What I'm showing you here is all the hurricanes since 1851, and it's seen from the viewpoint of Antarctica. You see South America there on the tip, and that band between the two blue-green zones is the tropics. So you can see for the most part, things stay in that band just below the tropics or above the tropics. And they generate a lot of disturbances. You guys might not see much of it, but those of us who live by coastlines, we get impacted by these. But in the grand scheme of things, they're not that, they're punctuations over a continuous excitation by the forcing winds in the atmosphere, the result of the Earth spinning around. You know, it's spinning around its axis, then it goes around the planet, and you have the differential thermal heating from summer to winter. That drives the whole ocean circulation. And the continuous driving force of the winds generates a continuous oscillation in the oceans. And it is, we call it the microbarum in the atmosphere, microseism on the solid Earth, and it just continuously vibrates. So what you're seeing here is the detections of all the different arrays pointing back to the sources of sound in the ocean. So the bright colors are the acoustic sound field generated by the ocean. And the little gray dots are stations, and they're pointing sometimes to storms, but sometimes they point to the whatever is closest and loudest. And that's not unlike us. If you're sitting right next to somebody who's loud, it doesn't matter if you have a concert next door, they're gonna really dominate your hearing perception. So our stations behave much like us. Whichever is closest and loudest wins. When you get a little closer to shore, those same stores and driving winds produce surf. And surf produces a lot of infrasound. You're watching right now essentially a 40-foot wave off the coast of Kauai. We had a nice big swell. We put some ocean bottom pressure sensors, and we deployed some acoustics as well as cameras, and we found a very nice association between the wave height, you know, and the infrasound. So the bigger it is, the harder it breaks, the more sound it creates. And any of you who've been by the ocean and been woken up in the middle of the night by, you know, big surf, we recognize this as a problem. So we went to Hawaii, to the north shore of Kauai, and you may or may not know about Pipeline. It's one of the most famous surf spots on the planet. It's where people go to become famous or get really hurt. Well, it's a beautiful, nasty wave that we thought wasn't surfable until about 40 years ago when the surfboards changed enough that people could do it. And so when we deployed an array over there, we found that Pipeline is one of the most efficient generators of infrasound. When that wave breaks, it just cracks. And every now and then we get a big swell, and Waimea Bay is the other place that is also famous for it. So again, whenever you have a big swell, our infrasound station just lights up, and it tells you where the closest, hardest station is breaking. Now let's step it up. We look at storms, we look at surf, and let's look at tsunamis. So Sumatra tsunami was one of the, actually it was the first time we found out that tsunami generating infrasound. So this was a realization point for us. And I show you the session in Diego Garcia, and when the Sumatra tsunami happened in 2004, we thought the station was toast because it's sitting just to the south west of the epicenter. But that island is so steep and in such deep water that the tsunami just ignored it. Essentially, it was too small relative to the wavelength, so it just passed right by. It barely produced an impact. So we got a pretty incredible record out of it. And so this is how we discovered it. We picked up the Sumatra tsunami signature in Diego Garcia, Madagascar, Kenya, Australia, and Palau. And at the time, that's all we had. And this is when we realized, oh, we have this deep infrasound signal that we can actually use to monitor these large events. Well, we wrote the book chapter on it, fine. Well, we need to revise it because after that, the Tohoku earthquake on tsunami, the one in Japan, took place and kind of blew our minds on what was actually possible. So you may recall the damage that the Japanese tsunami caused. How many of you saw the movies and the impact of it?
Oh, yeah.
so that pretty much took center stage. What few people know is that Santa Cruz, California, and Hawaii got slammed pretty hard too. We had a house picked up 20 feet, elevation inland, just picked up and taken out to sea. A few hotels are still closed and damaged from that. And what I'm showing you here is on the lower right-hand side, that first oscillation is from the seismic and the arrivals coming in from the tsunami. On the later arrival, that's a wall of sound coming in from infrasound, but arrive about 4 hours before the tsunami did. So we have tsunamis move at 200 meters per second. Sound is more like 340 meters per second. So the further you are, the higher a chance you have of getting early warning that it's incoming. And so this is something that, because we don't get that many tsunamis very often, we just start to collect the data on it. This also opened up the possibility of looking at waves up in the ionosphere. So, okay, there's not much atmosphere around 200 kilometers, right? So you think it's so light, there'll be no sound there. But there is a total electron content concentration up in the ionosphere. And those little electrons actually behave like a fluid, and they propagate sound waves up there. So we're using GPS systems, we're using other ionospheric sounders to actually look for waves in the outer reaches of the atmosphere, pretty much lower space. And so this event kind of kickstarted that technology, as you could see these waves moving through a GPS network. And so once again, going back to the point that we have, if you go deep enough in sound, everything reverberates. Everything's connected. You get normal modes of the Earth, and that affects the atmosphere, and that affects the ionosphere at a pretty high levels. And so you can no longer isolate one particular wave type. Now you're dealing with solids, liquids, gases, and plasmas. And that gets really fun up there, because now you're dealing with the couple Navier-Stokes and Maxwell's equations. And it gets really interesting in terms of the physics and the possible solutions that you can get out there, and the different types of waves that you can couple between mechanical and electromagnetic waves. So let's look at the biggest explosion we've had since the Cold War in the atmosphere, the Chelyabinsk meteor. So it happened over Russia. As I mentioned earlier, it had about half a megaton of TNT equivalent explosion, of about a little bit over 1 megaton, a nuclear equivalent. And it also blew up right over former nuclear facility, Soviet nuclear facility. They used to enrich plutonium and other nuclear materials over there. So imagine what would happen if this happened over the US, right? This blew up over Los Alamos or any other places that so you can see a lot of people were very nervous for the first few hours of this event. What was that? Are we under attack, right? This thing came from space, out of the blue. Nobody saw it coming. If you remember the narrative around here, we have a near asteroid path that everybody was looking for. And this time, this thing just came out of the blue, came out of the sun, essentially. We're blind to it. We got a few of these. We get Hiroshima year explosions per year, hitting the pancake into the Earth. And these bigger ones are a little bit less frequent, but we are revising how often we get them, because we are detecting more and more as we go. So one of our colleagues took the lead on a few of the papers on this. These are the detections over the global network for that meteor. And some of the stations didn't record anything because it was noisy. Some of the stations were down. Some of them were downwind. Some of them were upwind. We picked them up all the way in Antarctica. So again, if you go back to YouTube, you can look at the Chelyabinsk sound wave arriving all the way in Antarctica, then wrapping around, going all the way back to Russia, and then back to Antarctica again. So he went around the world at least twice. And so what you're seeing next, this is the model detection of the first Great Circle path. And the white, yellow are low attenuation, a combination of both diurnal, essentially ducting in the stratosphere, thermosphere, diurnal effects from day to night, and radiation patterns. Every time something blows up, it's easy to assume it's isotropic, everything radiates equally. But when things are moving fast, that's not the case. They're more like cylindrical. You've all seen the Mach cones from supersonic jets, right?
Yeah.
If you keep making that faster and faster, it all contracts into a cone. So there's a radiation pattern of these hypersonic objects. Essentially radiates perpendicular to the propagation path, except right in the front. Everything squeezes over there. So what you're seeing is the detections in blue, the non-detections in white, and the effect of the radiation pattern, with yellow being the least attenuation and red being the most attenuation. What we have is a decent match between model and expectations. So now we're going to synthetic type of listening, right? Mm-hmm. This is the part where you start modeling the environment around you, where you start playing with the sound field and saying, okay, how well can we match to your observations? Now, this is a complicated problem. This is a complicated problem on Earth where we can make measurements. But there's sound fields everywhere. There's sound fields in Mars, Venus, heck, space stations. And we have the ability to model these things. So this is the part where we enter where you guys, students, are in a place that is unprecedented. We didn't have this. Will and I didn't have this when we were going to school. We have the computing power to create a whole parallel universe where we have a model Earth that we can inform with real data and test our evaluations on those, and then compare observations with data with models. And not only that, we can start running signal processing algorithms on our parallel model Earth, and then compare those with observations on the real Earth. So this is happening at various disciplines, in particular climate change, climate studies. At present, we have over 30 years of continuous measurements of the atmosphere. So you start looking for global cycle oscillations. And I think we're going to see this more in geophysics and other physics types applications, not only on our planet, but possibly beyond that, which, as we know, at some point we need to explore. So I'd like to give you with the thoughts that we're looking at sound fields from primitive forces in this lecture. But there's also far more tangible things. We have spacecraft. We have industrial applications for this. They have an impact on how we live every day, and there are disturbances on it. And so now we have the technology to receive early warning. One possible application will be tornadoes also. We have avalanches, landslides. Anything that's big and voluminous and moves at sufficient velocity can produce this type of signatures, and you can use them to become more aware of the world around you. Well, and that's all I have for now. Thank you.
Thank you. Well, at this point, we should open up the floor to questions. So if you're listening online, we'll be watching the Twitter hashtags GHO seminar, as well as the hashtag Acoustics chat. Feel free to tweet at those hashtags, and we'll be paying attention to that. Or if you are on Google+, we're watching the comment thread there, and so you could post into the comments for the Google Hangout. We'll turn on the Q&A feature associated with the Google Hangout. So open the floor to questions. Do we have any questions here from our local audience? All right, Lucas.
I have a quick question. There was a period where we kind of lost you again during your slideshow, and I got a little bit lost with the, we're talking about the pattern with the explosion of the meteor and how it kind of shifted with the detection versus radiation fallout. If we could go back to that map and take a look at
Give me a moment. Yep, get in there.
was that calculated, or was that actually detected off the route?
Your question is very fair. This is a really complex product, actually. Let me get that on the screen. Just a moment. Need to get the little handle on the side. There you are. Okay, so what you're seeing is a combination. So the blue triangles essentially tell you there was a detection there. And the background colors are model results. It's a comparison between observations on a very coarse scale. Are the digitals really is yes or no, right? And
Right.
then the combination of what happens with the diurnal, it's just stations just get noisier during the day. You know, all the thermal effects kick in, the wind starts kicking in, and so detection capability goes down. And so that's one of this is the diurnal effect. Deducting is, you know, wind affects propagation, and you get better reception than wind and upwind. And so that's built into there. And then directivity is the part where you got this hypersonic, ridiculously fast source radiating perpendicular to the direction of propagation. And that is the other component that's built in there. So what you're seeing is a composition of all those three contributions to the sound field. And it is a complex process, so I'll leave it there for you to look in more detail. And I can also send you guys, so there's a reference to the paper that's in press now.
Yes, that'd be great.
That'd be fantastic. Thank you.
Okay, you're welcome.
Wow, that's beautiful. All right, Charles.
I have a question. Just out of curiosity, how did you get into infrasound as a research topic?
I was walking around this volcano in Costa Rica, and it was like really crappy weather. It was like raining and thunder, and it was really confusing. You couldn't see anything. There was a volcano in the clouds, and I knew it was there, but I couldn't see a thing. But I could hear it. And I could hear the difference between thunder, between howling monkeys, and a volcanic eruption. And I could hear the rocks rolling down the mountain. And so I realized you could use this stuff. You know, this is a way to find out what's going on when you have to run blind, or you're going at nights, or you know you have just obstacles to your vision. This provides you a really good estimate of it, of what's going on. And then I realized at the time how little work had been done in this field. And you know, you're a student, you're looking for something that's new and fresh, right? So I figured, oh, this is for me. And so this is kind of how I embarked in there, and it's been a very satisfying thing. And one thing I have to stress on you guys is sometimes it takes seriously 15 to 20 years between inception and realization of an idea into the accepted tools of monitoring. And so I urge you to be patient. There's once you come up with a new idea, it will not be embraced at first. In fact, in one of the stages, you'll be ignored at first by rule. Then you get resistance. If you get resistance immediately, you're doing really well. And then you'll be imitated, and then you've won. So it's nice to see that now people are using volcano infrasound as one of the standard tools that can be used under various circumstances. And so now looking for many other ways of doing this, and also giving people the opportunity to do it themselves. So next time you go somewhere cool that's really loud, you can pull out your phone and record it and say, hey, look, last time I was an Old Faithful geyser, right?
Mm-hmm.
I mean, we just turn it on, record it, and say, here it is. That's what it sounds like. So you have a thunderstorm, turn it on. You have fireworks, turn it on. You can actually capture this and provide additional coverage. You know?
Yeah, to me, that's really remarkable. I mean, the global infrasound network is nice, but you know, those are very spread out. It's really hard to get a denser network of an array of detectors. But using the barometer on the cell phone, you're able to also and so that's a really clever way to do it.
Thank you.
I have a question about that app, actually.
All right, Lucas.
So if we do download this app, I don't know how much you know about it, but To me, it seems like it would be kind of cool if, we collect the data, say for like a storm or if we live on the coast of a hurricane. Does it get sent to like a big database where you guys can actually look at the data and use that instead of just the set or just the station?
I'm getting a little off on audio. Could you repeat the question? I missed some of the chunks because it was. Sorry, we're getting audio issues from your end. Could you repeat the question, please?
So with the cell phone, like it's cool to just look at it, but does it automatically get sent to a larger source where it can be used in sort of like data, or is it just kind of like throwaway data in terms of being usable as far as?
Yes, it automatically streams to a server, and the processing begins automatically. So we're building it. If you go to the App Store and then you'll see the web page where it's being automatically streaming to. Right now it's ubiquitous.isla.hawaii.edu. And so you get to see the growth of organic growth of a global network just with cell phones. And so, yeah, we're trying to make this into a crowdsourcing type of global monitoring system.
Awesome. Is it also on like Android or is it just Apple?
We started with Apple. We started with Apple because there's more hardware configuration control on that, but we're already started on the Android version. It's just a lot more diversity on the configurations for that.
That does make sense.
Right. So he wrote it. So we've got a question on the hashtag. Black Physicists has asked the question, infrasound implies there is suprasound. What would be some applications of the latter?
Suprasound. That'll be like beyond sound, or can you clarify what you mean by suprasound?
I don't know.
Well,
I think he would definitely know about ultrasound, but I'm wondering what he implies there about suprasound. Let's respond back and we'll see if we can get a clarification.
Okay, I'll Google it in the process.
Okay, any other questions here locally? All right, Lucas.
So while we're Googling Supersound, could you give us a little bit more on your background and maybe what you did as an undergraduate? Because you said that you got into infrasound when you were walking along Costa Rica. How did you get to Costa Rica to walk along a volcano? Because I've never seen a volcano.
Yeah, I started with space sciences and astronomy, and then I got lured into the earth sciences. But my wife is an oceanographer, so she probably had an effect. And in the process of doing so, part of the thing that frustrated me a little bit about astronomy was that I couldn't really test my hypothesis very well, because everything was so far away. And so I wanted to really be able to verify that my assumptions were correct. And the earth sciences allowed me that. And it's when I started with oceanography, looked at seismology, and again, a beautiful field. A lot of the basic problems have been solved already. And when I started with infrasound, it was an exploration. I got out of grad school, there were like maybe 5-6 people on the whole planet doing it, right?
Mm-hmm.
So I got really lucky that the Comprehensive Nuclear Test Ban Treaty for monitoring clandestine nuclear tests started in 1996. And so we had a really unique opportunity, and it pretty saved my career, to actually build a global network. So that global network you saw there, we kind of helped design it and build it. And that was a really exciting time. Now it's become an accepted technology, and now you're looking for different things. So how I ended up there, it's kind of curious. It was like a detour from physics, but now that we're looking at waves in plasmas, it's kind of like going back full circle. So I'm going back to kind of space sciences and looking at the physics of those environments. So once again, there's nothing wasted really. Learn a lot about signal processing, and some of those tools can be used in any application and on any time scale. So wherever you go, you follow your heart, and wherever your curiosity goes, and you'll probably figure it out,
Okay, so we have clarification on what he meant by that.
Cool.
So supra basically means above the hearing range of the detector.
Oh, yes. Above the hearing range of the detector. We definitely, if it's referring to, by above you mean the saturation level of the detector. Yes, there'll be some signatures that will be beyond what our detectors right now can pick up. I have a colleague who just landed some sensors that he puts in balloons, high altitude balloons, Danny Bowman. He'll probably make a good guy for your lectures. And so he just landed those things, and testing those sensors is a real challenge. It's really cold over there. There's not much pressure, and strange things happens to sensors, And what happens when you put this on Venus? So a part of the challenge is to design a set of sensors that covers the targets of interest. If you know what the targets are, what the signatures are, you can really tune the system to that. But if you don't, that falls, the suprasound, it falls under unknown unknowns, right? If it's outside of your sensor, how do you know it's there? And so yes, there's a lot of sounds that we have not discovered yet. And that's pretty exciting. And that has to do with the sensor technologies that we apply to them. I don't think we'll be able to put a microphone at 150 kilometers. I could be wrong, but it might not be the best way to measure it. Now we're looking at ionospheric sounders and GPS sensors to measure waves in space, essentially, that we couldn't have measured with microphones. So that maybe is what he's referring to. Sound that is beyond our usual transduction mechanisms that we need to explore somewhere else.
The calibration of those microbarometer detection arrays is pretty complicated. Could you talk a little bit about how those things get calibrated, or do they do any sort of sensor normalization?
Yes, we have a number of active groups trying to standardize how we do this. And we have a number of different sensor technologies too that are evolving rather quickly. And so we try to use the reference frequency for audio applications is 1 kilohertz. That's kind of useless to us. So we have to go down to the 1 hertz type range, and then develop calibration sources for those frequencies, and then develop traceable standards. So it becomes a whole NIST and ASA reference standards process. And so we have initiated that, but it's not done yet. It's in progress. It's complicated, and it's not fully standardized yet. And so there's a lot of room there for contributions. Yeah,
I've seen large vacuum vessels, pressurized vessels that they put the sensors into, and then they have to slowly change the pressure inside those sensors, inside that pressure chamber to get the 1 hertz or the 1/10 of a hertz signal. Where on the planet, I guess, do research scientists study infrasound or do this kind of research? What sort of institutes do you know of?
The official calibration center for the nuclear monitoring technology in the US is at the Sandia National Labs.
Okay.
And we often use decompression chambers, right? What you use for divers when they go a little bit too fast, you have to put them in a chamber and recompress them again. And so that is one facility that does that for nuclear monitoring. But we also have other facilities that have to be able to change the ambient pressure. And for example, NASA or other folks at Naval Research Lab. And that is for space testing, right? You have to put them like in super low atmospheres, so the opposite of compression, and then make sure that all the inners don't explode during those conditions, right? So that's a different calibration situation where we had to put them at like 40 below zero and essentially a sub millibar pressures to see if the system will actually operate at all in those conditions. And so the calibration procedure has to be tuned to your environment of interest, whether it's on Earth or nearly out of this Earth or a different planet. That complicates things a little bit.
Well, what advice would you give undergraduates?
It's a brave new world out there, and learn how to code, guys. If you haven't done so already, you know, theoretical physics is beautiful, and I started with that at a time when you had no computing resources. That was the way to do it. It's good for benchmarks, but real life problems are complicated, and you're gonna need to solve them with a machine. And it's good to be able to do that. And go back to your physics. You need that because you can get a lot of shortcuts that way. So the math is good for algorithms. You'll need it. But most real-life physics problems are going to be solved in a computer. And so it's good to be at least well-versed in whatever language of choice you think is useful. C is a good core language because everything's kind of built on top of that, including Linux. Python is really versatile. MATLAB is nice too if you need to start there. But this will be a very useful skill for any of you.
Yeah, I'm always advocating it, but it's great to hear a professional talking about the same thing. So what do you have coming up? What's some of the next research or experiments you're going to be doing, or data that you're looking forward to that's coming out, or things that are happening? And then the follow-up question is, what's the next Acoustical Society meeting you'll be able to attend?
Well, let me start with inversely. The Acoustical Society of America, in joint with the Japanese Acoustical Society, is going to be in Hawaii next year, and we're hosting a session on infrasound. So come on down. It will be November 2016.
I think travel would be difficult. Unfortunately. I got to write the grant, my chair says.
Yeah, if you start saving now, it should be all right.
Okay. So what things do you have coming up on your radar there that is interesting?
Well, there's been a few. There really is something going on somewhere all the time.
Yeah.
So just this week we had a meeting with Bangkok. Last week we have a Soviet satellite fly right over Hawaii, and we picked it up on not only traditional sensors but also the cell phones. And then we're still working on that Chinese Tianjin explosion.
Yeah.
That was pretty tragic, and a very interesting situation because that could happen anywhere.
Yeah.
And our goal is to be able to provide useful information within seconds to minutes that an event happens. Early situational awareness. And again, if something happens in your neck of the wood, I want to be able to build an interface that you can log on to that server and process right there on the cloud. There's no way I can satisfy everybody's curiosity.
Yeah.
But I should be able to give you the tools to do it yourself. So if something happens around you, you should be able to scan whatever sensor networks are the closest to you and to be able to derive some useful information about that. And that's kind of the end game for me for the next 5 to 10 years, to build that infrastructure so you can do it yourself.
That's cool. That's really cool. So are there any openings for grad students there at your research lab, or that you know of that are unfilled that could use a smart physics major to jump in?
Yeah, actually, I just brought in a physics major for one of our research grants, and I have a computer science major, both PhD students right now. So yeah, there's opportunities, and so we go through cycles, end of year kind of thing. So keep your eyes open for these things, and let me know if anybody's interested. It's a relationship building thing. A PhD program is it's a 6-year commitment, and it's a way of building relationships. So that's my advice. A little advice to you. Science is about the people that you work with. Really, it's a community, and build those relationships. Be aware that you're dealing with people. You don't deal with organizations, you don't deal with institutions, you deal with individuals within those organizations. So you have to build trust, you have to build reputation, and the sooner you start doing that, the better it is for you. You can just continue that track over your career.
Fantastic. Do we have any other questions here locally?
I do have one question.
All right, fire away.
You mentioned it a few times about, I guess, the ionosphere and plasmas, and I guess the infrasound that I guess carries from the Earth up into the atmosphere. What exactly are y'all looking for in that?
You know, it's funny that's one of those questions that we're still kind of scratching our heads about, because we noticed the end member, and one of the goals of my colleagues with the balloon measurements is to figure out what happens in between. So you have these earthquakes or explosions, and they somehow make it to the ionosphere and couple down, but the exact mechanisms of how it gets there, it's kind of like a pretty open question right now. So there's a lot of time and effort going into figuring out how this happens, and it's going to be a question for the next 5 to 10 years. So it's a very timely question. I don't have a good answer for you.
Okay. Well, those are the good kind of questions to ask.
Exactly. Those are the best ones. Inquiring minds want to know.
Well, if there are no other questions, I want to make sure we thank our speaker for the time. All right, thank you very much. This has been fantastic. Really appreciate you taking time out of the middle of your day to chat with us. And I look forward to emailing you and seeing a few more things that you've got coming up on your research agenda.
Okay, thank you very much. It's been a pleasure.
Thank you. Bye-bye.
Aloha.